What is beyond the universe? It is a question that has haunted humanity for thousands of years. Long before telescopes, before Einstein, before we even understood what stars were made of, ancient civilizations looked up at the night sky and wondered, where does it all end? The Babylonians asked it, the Greeks debated it, medieval scholars wrestled with it, and today, with all our advanced technology and sophisticated mathematics, we are still trying to wrap our minds around it. This is not just another space mystery. This is the ultimate boundary question, the question that sits at the edge of everything we can ever hope to know. It is the question that forces us to confront the limits of reality itself. But here is where things get strange. Before we can even attempt to answer what lies beyond the universe, we need to define what we mean by universe in the first place. And this is where the whole question starts to fall apart. Think about it for a second. If the universe means everything that exists, then by definition, nothing can exist outside of it. Because if something existed out there, it would automatically become part of the universe. The moment you discover something beyond the edge, that edge moves. The boundary expands to include the new discovery. It is like trying to catch your own shadow. The harder you chase it, the further it moves away. Even the concept of absolute nothingness does not save us here, because nothingness is still something. It is still a state of existence. A vacuum is not the absence of reality. It is a type of reality. Empty space still has properties. It can curve. It can expand. It obeys the laws of quantum mechanics. So even if you imagine a vast emptiness beyond the universe, you have just described another region of space, which means it is part of the universe now. This creates a logical paradox that philosophers and physicists have struggled with for centuries. If something exists beyond a boundary, it becomes part of what is inside the boundary. The universe is not a box sitting in a larger room. It is not a bubble floating in an ocean. Those metaphors require an outside perspective, a place to stand and look at the whole thing from a distance. But there is no outside perspective for the universe. There is no place to stand, because every possible place you could stand is already inside the universe. So asking what is outside the universe might actually be a meaningless question. It is similar to asking, what does the colour red sound like, or what shape does happiness have? These questions use language in a way that seems to make sense, but they are actually mixing incompatible categories. You cannot assign a sound to a colour because sound and colour are fundamentally different phenomena. They do not overlap, and in the same way, you cannot assign an outside to the universe because outside requires a spatial relationship that only exists within the universe itself. This confusion comes from forcing human intuition onto cosmic mathematics. Our brains evolved to navigate forests and hunt animals and build shelters. We are designed to understand medium-sized objects moving at medium speeds in three-dimensional space. We are not designed to understand infinity. We are not designed to grasp the concept of space-time curvature or the limits of causality. When we try to imagine the universe, we instinctively picture it as a giant sphere floating in darkness. But that mental image is misleading. The darkness around the sphere is already space, and space is what the universe is made of. The problem is not the universe. The universe is doing just fine. It exists, it expands, it follows the laws of physics. The problem is how we define it. The problem is the limitations of human language and human thought. When confronted with something that operates on scales and principles completely alien to everyday experience, we are trying to use words designed for talking about objects and places to describe something that is neither an object nor a place. We are trying to use logic designed for finite systems to understand something that might be infinite. And here is what makes this even more fascinating. This is not just a philosophical puzzle. This is not just ancient thinkers sitting around debating abstract ideas. This question has real implications for modern physics, because depending on how you define the universe, the laws of physics might behave differently. If the universe is finite, certain equations produce one set of answers. If it is infinite, they produce another. If it wraps back on itself, the mathematics changes again. The way we answer the question, what is the universe, directly impacts our understanding of gravity, expansion, quantum mechanics, and the fate of reality itself. The answer might be nothing. Not nothing in the sense of empty space, but nothing in the sense that the question itself does not compute. It is like asking what happened before time began. Time is the framework in which before and after make sense. Without time, the word before has no meaning. In the same way, space is the framework in which inside and outside make sense. Without space, or beyond the limits of space, the word outside has no meaning. But do not think this means we have reached the end of the conversation, because there is another way to approach this question. Instead of asking what is beyond everything, we can ask what is beyond what we can see. And that question has a very different answer. That question takes us into the difference between the observable universe and the actual universe. And once you understand that difference, everything changes. The whole perspective shifted. The question stopped being what is beyond everything and became what is beyond what we can actually see. That change sounds small, but it is enormous, because now we are not talking about pure philosophy. Now we are talking about something that can be described with physics, distances, and real data. Ask a new version of the old mystery. When you look out into space, how far are you actually seeing, and what is hiding just beyond that invisible edge? Start with a simple fact. The universe is about 13.8 billion years old. That number is not a guess. It comes from studying the afterglow of the Big Bang, the cosmic microwave background radiation, and the way galaxies move and cluster over time. Light does not travel infinitely fast. It moves at a fixed speed, about 300,000 kilometers every second. That speed limit creates a horizon around us. Not a physical wall, not a shell, but a limit to how far light has had time to travel since the beginning of the universe. Anything farther away than that horizon has simply not had enough time to send its light to Earth. Imagine lighting a candle in a dark room and waiting. The light spreads outward, but after a certain amount of time it has only reached a certain radius. There may be objects beyond that radius, but their light has not reached you yet. They exist, but as far as your eyes are concerned, they are invisible. That is exactly how the observable universe works. The observable universe is the region of space from which light has had enough time to reach us since the Big Bang. It is like a sphere centered on Earth, but not because Earth is special. Any observer anywhere in the universe would have their own observable sphere around them. Here is the surprising part. You might think that if the universe is 13.8 billion years old, the radius of the observable universe should be 13.8 billion light years. But the real number is much larger. The observable universe has a diameter around 90 to 92 billion light years. That sounds impossible at first. How can we see something that far away if the universe is not that old? The answer is that space itself has been expanding the entire time those photons have been traveling. While the light is moving toward us, the fabric of space is stretching, increasing the distance between us and the source. So the galaxies that sent us that ancient light are now much farther away than they were when the light started its journey. This leads to one of the most mind-bending ideas in modern cosmology. What we see is not what is actually there right now. When you look at a distant galaxy near the edge of the observable universe, you are seeing it as it was billions of years ago, when it was much younger and much closer to us. The real galaxy, as it exists in this moment, has moved to a new position in a larger, older universe. The observable universe is not a snapshot of reality now. It is a layered time machine with nearby objects showing us the recent past and distant objects showing us the deep past. So what lies beyond that observable edge? Almost certainly, more galaxies, more stars, more clusters, more structure. The current standard model of cosmology, supported by detailed measurements of the cosmic microwave background and large galaxy surveys, strongly suggests that space continues beyond what we can observe. There is no sign that the universe simply stops at the cosmic horizon. The simplest interpretation is that the same pattern of matter and energy extends outwards, perhaps for an unimaginably long distance, possibly forever. To picture this, imagine standing on the shore and looking at the ocean. Your eyes can only see to the horizon, where the water seems to meet the sky. That line feels like an edge, but you know it is not. You know that ships can sail far beyond that point, that there are entire continents you cannot see from where you stand. The limit is not in the ocean. The limit is in your perspective. The cosmic horizon works the same way. It is not a physical barrier in space. It is a boundary created by the finite age of the universe and the finite speed of light. Yet the human brain does something tricky here. Because we experience the cosmic horizon as an edge in our data, it is very easy to start imagining it as an edge in reality. It feels like there is a shell, and beyond that shell there is nothing. But there is no cosmic glass wall where galaxies crash and stop existing. Objects beyond the horizon continue moving, colliding, forming stars, and evolving in ways we will never directly see. They simply exist beyond our light cone. The universe does not care that we cannot watch what is happening there. This raises a deeper emotional question. Are we comfortable living in a universe where most of reality will forever be beyond our reach? The observable universe is already huge, but compared to the possible full universe, it might be like a tiny island in a vast, unending ocean. Even our most powerful telescopes are limited by this horizon. No upgrade, no new technology can break the speed of light or rewind the age of the universe. There is a built-in limit to what any civilization, anywhere, can ever observe. But if that sounds discouraging, consider the flip side. The very existence of an observable universe is what makes cosmology possible. The fact that light takes time to travel allows us to see the universe at different ages, at different stages of its evolution. It allows us to test models of how structure forms, how dark matter behaves, how dark energy drives expansion. The cosmic horizon is both a limit and a tool. It blocks us from seeing everything, but it also reveals how everything has changed over time. So when someone asks, does the universe end where our telescopes stop seeing galaxies, the answer is almost certainly no. What ends is our access to information. The universe does not end where our vision does. Is the universe infinite or finite? What is its shape? Can something be finite yet have no edge at all? To answer those, we need to talk about expansion, curvature, and the shape of reality itself. We drew a line between what exists and what we can actually see. That line was the observable universe, set by the age of the cosmos and the speed of light. Now the mystery deepens. Even if we accept that there is more universe beyond our horizon, a new question appears. What is the universe doing as a whole? Is it infinite or finite? Does it have a shape? And if it is expanding, what exactly is expanding into what? These are not just poetic questions. Modern physics has very specific, very strange answers. The turning point came in the early 20th century. In 1915, Albert Einstein published the theory of general relativity, a completely new way of thinking about gravity. Instead of treating gravity as a force that pulls objects together, general relativity describes gravity as the curvature of space-time itself. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. When Einstein applied his equations to the entire universe, he ran into a problem. A static universe, one that just sits there unchanging, was not stable in his mathematics. Space-time wanted to either expand or contract. At first, Einstein did not like that result. The idea of a changing universe felt too radical, so he tried to force his equations into predicting a static cosmos by adding something called the cosmological constant, a kind of anti-gravity term that would hold everything in place. But the universe refused to cooperate. In 1929, Edwin Hubble studied light from distant galaxies and noticed that almost all of them were redshifted. Their light was stretched to longer wavelengths. The farther away a galaxy was, the more its light was shifted. The simplest explanation was that space between galaxies was expanding. Galaxies were not just moving through space. Space itself was stretching. This is the first crucial idea. When cosmologists say the universe is expanding, they do not mean it is expanding into some pre-existing empty room. There is no outer container waiting to be filled. The distances between galaxies grow because the metric that defines those distances changes with time. A good way to picture this is to imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because they are crawling over the surface, but because the surface itself is stretching. There is no need to ask what the balloon is expanding into if you are a two-dimensional creature living only on its surface. The expansion is a change in internal geometry, not an explosion into an outside. As space expands, light travelling through it gets stretched, leading to redshift. Over very large distances, expansion can happen faster than light can cover the gap, which is one reason regions can slip beyond our observable universe, even though nothing is locally breaking the speed of light. The expansion is not motion through space in the usual sense. It is the dynamic behaviour of space-time itself. This is why asking what the universe is expanding into is like asking what is north of the North Pole. The question assumes a larger background that does not exist, but expansion is only half the story. To understand the full shape of reality, we also need to talk about curvature. General relativity allows the universe to have three possible large-scale geometries. It can be positively curved like the surface of a sphere, negatively curved like a saddle, or flat. These words describe how straight lines and triangles behave on cosmic scales. In a positively curved universe, parallel lines eventually meet, and the sum of the angles of a large triangle is more than 180 degrees. In a negatively curved universe, parallel lines diverge, and triangle angles add up to less than 180 degrees. In a flat universe, Euclidean geometry holds, and those angles add up exactly to 180 degrees. Astronomers measure this curvature using several independent methods. One of the most important is the pattern of tiny temperature fluctuations in the cosmic microwave background radiation. These fluctuations act like a standard ruler imprinted on the early universe. By comparing the apparent size of that ruler at different distances, scientists can infer whether space is bending on large scales. The current data show that the universe is extremely close to flat, with any curvature being so small that it has not yet been clearly detected. Here comes the subtle and mind-bending part. A flat universe can still be finite in size. Flat describes local geometry, not global topology. Imagine wrapping a rectangle of paper into a cylinder. On the surface of the cylinder, the angles of triangles still add up to 180 degrees, and parallel lines stay parallel. The geometry is flat, but the space is not infinite in all directions. You can travel around the cylinder and eventually return to where you started. In the same way, the three-dimensional universe could have a topology that loops back on itself. You might travel in a straight line for long enough and eventually come back to your starting point without ever encountering an edge. This possibility leads to another fascinating scenario. The universe could be finite, yet have no boundary, no walls, no outside, no place where the universe stops and something else begins. Just as the surface of a sphere is finite in area but has no edge, space-time itself could be finite in volume but unbounded. If that is the case, then the question where is the edge of the universe has the same answer as where is the edge of the Earth if you only move along the surface. There is no edge. You can keep going forever and only loop around. So now, our earlier questions become sharper and stranger. If the universe can be expanding without expanding into anything, and if it can be finite without having an edge, what does that do to our intuition about beyond? The expansion of space and the curvature of space-time are perfectly self-contained, yet the curiosity does not go away. If anything, it grows, because if the universe can be self-contained, if it does not need an outside, then the next big question is why there is something rather than nothing. What set this expanding, possibly finite, possibly infinite structure in motion? And if there is no edge in space, is there an edge in time? Now we will push that idea even further and ask whether the universe needs an outside at all, not just physically, but conceptually. We will explore why modern cosmology suggests there may be no edge, no outside, and perhaps no problem with that. By the time we reach this point in the story, something important has already shifted in how we think about reality. Now we have to face the conclusion that all of this has been quietly pointing toward, Maybe the universe does not need an outside at all. Maybe the need for an edge is not a property of the cosmos. Maybe it is a property of the human mind. Start with the idea of a finite universe. Intuition screams that if something is finite, it must have a boundary. A room has walls, a book has a last page, a country has a border. But mathematics does not share that intuition. A classic example is the surface of a sphere. If you walk in a straight line on the surface of the Earth, you can keep going forever, circling around and around, and you will never hit an edge. The surface area is finite, but there is no boundary line where the surface ends and something else begins. When cosmologists build models of the universe, they can do exactly the same sort of thing, just in 3 dimensions instead of 2. A 3-dimensional space can be finite and unbounded. There is no need to place that space inside a larger container. This is the part where our imagination rebels. We almost cannot help picturing the universe as a ball floating in some larger emptiness, like a snow globe in a vast dark room. But that picture smuggles in an outside by accident. The moment you imagine the universe as a ball, you have already placed it inside another space, and that extra space now belongs to the universe by definition. To avoid that trap, it helps to think more like a mathematician. The universe is not a ball in space. Space itself is the thing being described. The equations of general relativity do not sit inside another dimension, watching space-time from the outside. They describe the geometry from within. There is no requirement for a larger scene. Some modern theories in physics do talk about higher dimensions or multiple universes. In some versions of string theory, for example, our universe might be a 3-dimensional slice of a higher dimensional structure. In some versions of eternal inflation, many bubble universes might form inside a larger inflating spacetime. These ideas are fascinating, and they make for great science fiction imagery. But here is the crucial point. Right now, most of these ideas are not directly testable. They are speculative attempts to extend our current theories to explain open problems, like the values of fundamental constants or the nature of dark energy. The known laws of physics do not require these extra layers. The equations of general relativity work perfectly well with a universe that is self-contained. This leads to a very unsettling but powerful realization. An outside view of the universe, the picture of the cosmos as an object you can look at from afar, is not mathematically required. It is psychologically tempting. It is visually intuitive. It feels comfortable. But the universe does not owe us comfort. Space-time can be entirely self-consistent without any external frame. Every event, every galaxy, every particle, every law of physics lives inside this structure. There is no balcony seat where some hypothetical observer watches it all from beyond the edge. So when someone asks what is beyond the universe, modern cosmology gently suggests that the question itself might be a category error. It mixes 2 ideas that do not belong together. Outside is a relation between regions of space. A park is outside your house. Space is outside your city. But the universe, as physicists use the word, is not a region inside a larger room. It is the totality of space-time and its contents. To ask what is outside the universe is like asking what is north of the North Pole or what colour the number 7 is. The grammar of the question is correct, but the concept it is pointing at does not exist. None of this means that imagination has no role. In fact, imagination is essential. Every major advance in physics began with someone daring to think about reality in a way that ordinary experience never suggested. Einstein had to imagine what it would feel like to ride on a beam of light. The early pioneers of quantum mechanics had to accept that particles behave like waves, and that probability is built into the foundations of nature. Cosmologists had to accept that space can stretch, that time can bend, that there was a moment when the observable universe was compressed into a much smaller volume. Each time, imagination had to give up some comfortable picture in exchange for a deeper, stranger truth. Here is where curiosity becomes a kind of superpower. The most productive questions are not always the ones that have clean answers. Sometimes the most powerful questions are the ones that force you to realize you have been thinking about the problem in the wrong way. What is beyond the universe turns out to be one of those questions. It pushes us to refine what we mean by universe. It forces us to distinguish between the whole of space-time and the observable patch we happen to inhabit. It makes us analyze expansion, curvature, and topology, and in the end, the answer is not a satisfying list of what lies on the other side of some cosmic wall. The answer is that there is no wall. Instead, modern cosmology turns the question around. The real mystery is not what is outside the universe, but how a universe like this can exist without needing an outside at all. How the laws of physics can close the system in on itself so that no external stage is required. Some physicists explore this through models of quantum cosmology, asking how space-time might emerge from more fundamental rules. Others study the detailed structure of the cosmic microwave background, looking for subtle signatures of curvature or topology that would tell us whether our universe loops back on itself. Each of these efforts is a way of asking the same thing in a more precise language. How self-contained is reality? And maybe the deepest shift is philosophical. For most of human history, people imagined the cosmos as a series of nested shells, the earth inside the heavens inside some larger divine realm. There was always an outside, always a beyond. Modern cosmology breaks that nesting instinct. It says the universe may be all there is, in a rigorous sense, and that this all does not sit inside anything else. At first, that can feel disappointing, almost claustrophobic. But look again. A universe with no edge is also a universe with no boundary to curiosity. There is no outer wall saying, beyond this point, your questions must stop. There is only the challenge that some questions, like what is outside the universe, must be reshaped before they can be answered. So the story that started with a brain-breaking question ends in a different place than it began. The question was never really about what lies beyond everything. It was about how far our concepts can stretch before they snap. The universe does not seem to need an outside to exist. It does not seem to require an edge to be real. The edge we keep running into is the edge of the human imagination. And that edge, unlike the cosmic one, is something we can keep pushing.